In the last two classes, I have discussed about ion implantation and doping. Today, what I am going to talk is about thermal oxidation of silicon. Silicon dioxide, which is grown on silicon substrate, is very important for fabrication of silicon-based devices. And what I am going to do today is to discuss about different oxidation process, how you can oxidize silicon dioxide, how you can control different thickness, and what are the different processes particularly, and then how do you use the silicon dioxide layer that you have grown for the fabrication of you know particularly silicon based devices like CMOS and any other. Now if you look at silicon wafer, then silicon wafer is actually have a oxidized silicon dioxide is normally silicon SiOx, so it is an oxide layer which is called the native oxide layer, and the thickness of this native oxide layer is something like 15 to 20 angstrom. So that's always there because silicon get oxidized if you keep it in the ambient condition. So this is sort of oxidized silicon wafer that you normally want. But for the fabrication of the device, this 15 to 20 angstrom silicon SiOx layer is not good for the device fabrication, and you need to grow really a silicon dioxide layer, thick dielectric layer, depending on the purpose. Now, what you do is that you can actually convert some of the silicon layer into oxidized layer and silicon dioxide layer, right? And this thickness can be really high, like 30 to 2000 nanometer. Excuse me. And when you grow this thickness, silicon dioxide thickness, you see that this is the thickness of the silicon uh, crystal which has been converted into silicon and made a thickness of this high. So that means you consume some of the single crystal silicon and then convert it into silicon dioxide layer, right? So that's very important, that when you consume some part of the silicon layer, but when you grow it, convert it into silicon dioxide, then thickness actually increases for obvious reason, because silicon get oxidized, and you have like silicon dioxide, two oxygen connected with silicon, and then therefore the volume actually increases, right? So as usual, so I start with the references. Basically this book I'm going to follow for this topic. Chapter 10, Oxidation, is the name of the chapter. Otherwise also I discussed in the earlier also that this book also is very good for other part of the discussion that we had earlier. You can also consult this. Now I give two more book. It's very important and very interesting book. uh, Harry Vendrick, both the author of both the books. So one is the Bits on Chips and other is Nanometer CMOS IC. So basically they are more advanced, book on the fabrication of MOSFET chips, chip and ICs. But you don't have to go through all those book, but I mentioned two chapters. Chapter 10 in this book, it's called Fabrication and Manufacture of CMOS from Nanometer CMOS IC. So essentially, my plan of the talk is, today's discussion is, I'll talk about oxidation, and then how do you use this oxidized silicon dioxide layer for the fabrication of device, and then most advanced CMOS devices, which are part of the IC, how do you use it. So basically covered by all three reference book is very important. Now, what are the properties of thermally grown silicon dioxide? So as I already discussed, that you consume some part of silicon and oxidized it. Now when you do this oxidation and then look at what exactly happens at around this space, then you see this. So this is essentially a cross-sectional transmission electron microscopy image. What you found is this part is essentially your silicon dioxide, and this is the silicon. So it is a lattice image, so you can see the silicon atoms. Now look at this interface. It's really extremely clean silicon interface. Now if you go from lattice image to SiO2, then you don't have any lattice image for the silicon dioxide, because this essentially an amorphous film, so there is no crystallinity in this. So it is called fused silica. So this is an amorphous in nature. Now if you look at these two numbers, which is density, it's essentially mass density, right? So mass density for SiO2 is 2.21 gram per centimeter cube, and if you look at the mass density for the silicon single crystal, which is little bit higher than silicon dioxide, because you incorporate oxygen into the silicon matrix, and therefore your density reduces. So a little bit mass density reduces. Now so there is also single crystal SiO2, which we call quartz, so but quartz has much higher uh, density, which is even higher than silicon. So 2.65 gram per centimeter cube. So this one is not amorphous. So this is a single crystal silicon dioxide. Now what are the other property of silicon dioxide? Is this amorphous, basically the fused silicon. So it's about zero thermal expansion. So thermal expansion is pretty low, which is very important for technological development, because the gate oxide layer, if you use silicon dioxide, thermally grown silicon dioxide as a gate oxide layer, then what is important is the capacitance. Now if temperature can expand the oxide, then of course its capacitance changes. So you need a dielectric layer which thermal expansion coefficient is pretty low. So silicon dioxide is a better choice in that case. Melting point is of course very high, around 1600 degrees centigrade, and so these are a few more numbers. So atomic density is 2.3 into 10 to the power 22 molecules per centimeter cube, whereas for silicon it is a little bit higher, because silicon dioxide is a bigger molecule. And then if you look at these two numbers, it's basically when you think about using this silicon dioxide material for particular application, whether it's optical and electrical applications. So there are two parameters which plays very important role. Refractive index is 1.46, which is slightly less than glass, and dielectric constant is epsilon, which is 3.9. So now this decides the capacitance, gate capacitance. So it's relatively high, not low. It's excellent electrical insulators. That's very important, because we use a dielectric material, so the resistance should be very high, resistivity should be very high, right? So 10 to the power 20 ohm centimeter, and it's a dielectric material, and that's where energy gap is really pretty high, so 8 to 9 electron volt. This is also very important, high breakdown electric field, because since you are going to use it as a gate dielectric, so the breakdown field should be very high for this kind of application. So silicon dioxide actually kind of property that you see here, actually the suitable material, one of the suitable materials for the fabrication of silicon based devices. What are the uses of oxide film? Yeah, there are many. So now see that what are the uses of oxide thin film. uh, there are several uses. The first one is device protection isolation. So silicon dioxide is used as an effective barrier to isolate and protect sensitive devices in silicon. So this is essentially this is the way it is done, that you grow a thick oxide layer between two devices. You have one device here, another device, your own device here, another device here, and just to isolate these two devices, you grow a thick oxide layer. So this oxide layer can be used as a isolation. Next is surface passivation, which is very important, as I discussed earlier as well, that you know it reduces the surface state density at the interface. Now, what exactly happens? Now, if you look at for example, the silicon crystal structure, and what you found here is these dots are silicon atoms, and they are connected by covalent bond. So when you have a covalent bond, means one electron from this silicon atom another is sharing with another electron from this. So each bond essentially has two electrons shared from both the atoms. Now when you actually cut this crystal, let's say along this line, so when you cut this crystal along this line, so you essentially make a surface, and then what you essentially make is a surface with unsaturated bond, which means that one electron, so every top exposed surface atoms will have one unsaturated bonds, and these are called the dangling bond. Now when you grow oxides on top of it, this dangling bond has to be saturated, otherwise you are going to have some excess charges at the interface, which will create problem in the device performance. So now when you do oxidation, then basically at the interface you uh, essentially reduce this number of dangling bond density, and therefore the surface states density also will be reduced. The passivation is important for controlling the leakage current of the junction device and growing a stable oxide layer. So this is also another purpose for oxidation, surface oxidation for silicon substrate. Third one is gate oxide and dielectric layer. So that is very common, and I have discussed earlier also that silicon dioxide is primarily used as a gate oxide, a thin gate oxide layer for MOSFET devices. And typical thickness for this gate oxide is of the order of 20 angstrom. And if you look at the design, typical design of a MOSFET device, where you have two contact, source and drain, and this is your gate, and here you have a thin layer, so this is the channel. So oxide layer can be used as a gate dielectric layer as well, because oxide is silicon dioxide, as I said earlier, that is a good insulator. Barrier to selectively introduce dopant into the silicon surface, right? So what you do is, like, let's say I want to just make, so you have a p-type substrate, this part you want to make as a n-type, other parts should be remaining there without any dopant. So you use you convert some part of the silicon substrate into silicon dioxide, and then when you implant it, so let's say phosphorus ion you implant, then this silicon dioxide layer we use as a mask, so such that you don't have doping in this part, but you can actually have doping in the silicon. So it's sort of like dopant barrier, so it's like a mask that you use. Dielectric between metal layers. So this is also another application of the silicon dioxide. So silicon dioxide is an effective insulator between metal layers of the microchip. So when chips are developed, you remember, you should understand that in the chip, it's not about one layer. So there are several layers are grown one after another, right? And they are connected. So all the devices are connected in a particular fashion. So how do you actually insulate different layers where you have different kind of circuitry design inside the chip? So this is also done by silicon dioxide layer. For example, let's say I have this is oxide barrier, so you have some diffusion resistor, and then just this region if you want to isolate by this metal layer, so you put an oxide layer, so then this metal actually is not connected to this part, right? Similarly, several layers are there, so these are passivation layers, so you can grow different layers, which I'll again explain later. This is called field oxide. The field oxide is also like isolation oxide. So what you do is that you grow a small region with a thick oxide layer, which is you see around 2500 to something like 150 15,000 angstrom. So it's a quite thick oxide layers, these two part. Actually these regions you are going to design, you are going to fabricate the transistor. So one transistor is separated by the field oxide. Now I summarize the various thickness of oxide layer required for a specific application. In this table, what you can see in this column, I have semiconductor applications, and here the oxide layer thickness in angstrom. Gate oxide, which is something like 20 to 60 angstrom. This is actually not very specific, but I know it depends on what kind of technology you are looking for. For example, 0.18 micron generation MOSFET, typically 20 to 60 angstrom oxide gate oxide layer thickness is used. Similarly, capacitor dielectrics, which is essentially around 5 to 100 angstrom, dopant masking oxide, right? So that's 400 to 1200 angstroms. This again depends on what kind of dopants that you are going to use, and what is the energy for the ion beam of the dopant atom, and temperature, time. So there are many other parameters that involves in deciding the thickness of this masking oxide, right? Then we have STI barrier oxide layer, which is something like 150 angstrom. STI is essentially a shallow trench isolation. This is a thick oxide layer that is grown to isolate different transistor. So similarly, low cost pad oxide also, which is around 200 to 500 angstrom, which is also used for the same purpose, like to isolate different devices. And the last one is the field oxide, which I already explained you what it is. This is also similar applications, like to separate out. It's like a isolator of isolator used between devices. This is quite thick, like 2500 angstrom to 15,000 angstroms. Is quite thick depending on the application. Now, thermally grown, oxide layer. As I said, that if you get this silicon wafer, it comes with naturally grown native oxide layer, but then you need to grow the thick oxide layers as per your requirement. There, the whole wafer can be oxidized. There are two different processes. One is called the dry oxidation, and another is called wet oxidation. And then, of course, there is another technique. So in this case, of course, whole silicon wafer you oxidize, but sometimes you need a very selected region to get oxidized, not the whole wafer, right? So that is called selected area oxidation, and that's called the local oxidation of silicon, as you said, the low cost. Similarly, you have shallow trench isolation, right? So shallow trench isolation is, it's sort of like, you see that uh, the shape of this oxide layer here, it is much more, sharp and thick oxide layer. So these are also separator. So you essentially have the device at this point. So this is again separator. Let us discuss about the schematic structure of amorphous silicon dioxide, which is called fused silica. Uh, if you look at the basic structure of silica, which is essentially contains one silicon atom and four oxygen atom, and they make a tetrahedral structure. Now this small silica unit actually make the silicon dioxide amorphous silicon dioxide. What you see here is this individual tetrahedral structures which are arbitrarily connected by, there are some bridging oxygen and there are some non-bridging oxide. So absolutely arbitrary connections of this tetrahedral, and in essentially it is more disordered structures, which I have shown you earlier. This is a cross-sectional TM microscope image which clearly shows the lattice image of silicon, and the other part which you converted into silicon dioxide, which clearly shows that it's amorphous in nature. But what you also can see here, as I said earlier, that you have a really excellent interface that you can visualize even at the atomic level. So that is also like interface can be charged as well. Now, what are the different process of oxidation process? Now in this case, if you want to oxidize only selected part of the silicon substrate, which is essentially required, instead of like oxidizing the whole wafer, you know uh, you can selectively oxidize a little part, and in that case you need to use a mask. So you mask the other side and get you oxidize this part. So to do this, so you have to like heat it at high temperature in presence of oxygen. Then this part of the silicon will get oxidized, and there can be dry process. So it oxygenate gas silicon dioxide, so it's directly make the silicon dioxide. And the wet process, what happens that you need to use water molecule, and then you get silicon dioxide solid. This hydrogen gas which actually is passing through the oxide layer, right? And the furnace temperature where actually growing is really high, right? So what you see here is that, as I told earlier, that some part of the silicon will be consumed and then make a oxide layer. So essentially your this part of silicon has been consumed, and this is the whole part of this oxide layer that has been grown, right? Now remember that in case of dry layer, so your whole silicon is consumed and get oxidized, but in the wet oxidized layer, so what happens is that this reaction takes place at the bottom, right? And this hydrogen gas that comes out, so that's coming from the bottom and it's coming through all the way through this silicon dioxide layer, and therefore the wet oxidized silicon dioxide can be a little bit more porous, right? So its property may not be very good like uh, thermal equivalent silicon dioxide. So yes, so which I already said that oxygen actually how this thermal oxide grows. So the oxygen actually grows the oxidize the first layer and then again diffuse the inside end. So that's how oxygen moves from higher to lower concentration region, and then it get oxidized, right? Now what is interesting is that how much of the silicon that you consume to grow how much thick. So that is sort of typically it was found that 45% silicon, right, is consumed to grow something like 100% the layer. So which means that if you have something like 1000 angstrom oxide layer, that means around 450 angstrom silicon layer you have consumed to convert it into 1000 angstrom silicon dioxide layer. Okay. Now, as I said, there are dry and wet oxidation process. So, the condition is, as I showed earlier, that you have to heat at something like really high temperatures, 900 to 1200 degrees centigrade. That's the furnace temperature. And in case of wet oxidation, which is much faster, almost 10 times faster than the dry oxidation process. In case of dry oxidation process, so oxide layer thickness typically like 0.05 to 0.5 half a micron. So this is, it's quite thick in case of when you think about the device. Excellent insulator, and for you can use it for the gate oxide layer. Now it may contains nitrogen to form oxynitride. So that's because the nitrogen gas is essentially used as a is a gas that carries the oxygen gas. So nitrogen is used, and so I'll talk about this. Now when you use wet oxidation wet process, so it is essentially less than 2.5 micron. It is thicker than that. It's also a good insulator for field oxide or masking. So normally wet oxide layers are used for field oxide or mask, not for the gate oxide. As I said, that the diffusion of hydrogen gas out of the frame may increase the leakage current, and therefore there may not be a good oxide layer for using it as a gate dielectric layer. Now, so now here you see that it's basically it shows that how much time you need. It's sort of like guideline that how much time you need to grow, what kind of thickness of thickness of the oxide layer, uh, using the dry oxidation process. For example, like 100 minutes, right? And which temperature, right? So 100 minute, if you grow something like here, right, in 1200 degrees centigrade. So point 0.1 is like 0.2, 0.3 micron thick oxide layer you can grow. So it's like a guideline that which temperature you should grow the grow the oxide layer, and then how much time, how much thickness of the oxide layer that you want. So this is for silicon 100 substrate. Now remember that this oxidation process also depends on the crystallographic orientation of the silicon substrate. What are the different methods for thermal silicon oxidation methods? So this is typically the horizontal furnace. So you have different zone, and you can use it for oxidation. You can use it for doping as well. So it can be, this furnace can be horizontal, or it can be vertical as well. Now what you see for the dry oxidation layers, as I said, that you need nitrogen to actually carry this oxygen gas. So you have a oxygen supply, you have nitrogen supply. These two gases come here, and so this is the furnace where you need to heat, and these lines are essentially the vapors, and at particular temperature this vapor will get oxidized. Okay. Now you have wet oxidation process also. There are two different is wet processes under wet oxidation. So wet oxidation and pyrogenic oxidation. Now in case of wet oxidation, see, all you need is again oxygen and nitrogen to carry the oxygen gas, and then here you have a water molecule, and then you heat them and then water vapor comes there because you need water to react with the silicon surface. And here is the furnace, and you can oxidized the silicon wafer using wet chemical process. There is another process which is called the pyrogenic oxidation process. So this is more popular. Now in this case, you remember that you need directly water, right? But in this case, you don't need water, but you actually need oxygen and hydrogen gas molecules. So there will be another kind of reaction takes place. So here it will be oxidized with oxygen and hydrogen. So become water molecule, and then it interact with the silicon substrate, and basically silicon wafer get oxidized. Now this one I showed earlier also. This is essentially the locus. This is oxidized silicon dioxide layers which separate out the device. So this is where the device which actually grow. This is the channel, typical channel length. So this is the channel length, but these are the separate, nothing to do with this. Okay. This is essentially NMOS, right? And the NMOS is around something like 1970s, right? But in this case, the gate length is typically something like 0.5 microns. It's relatively bigger. So how do you grow these ones? This oxidized low cost layers. So what you do is you know so you have silicon substrate, and then you have silicon dioxide layers, like thin silicon dioxide layer that you have normally the native oxide layer. And then all you do is that you grow another layer which is silicon nitride, and this is essentially a mask. So you essentially want to cover the silicon substrate, and selectively some part you want to grow. Now all you need actually a couple of masks. So essentially 5 masks you need for whole process, right? And so essentially that this is one mask, then this is another mask, this is another, this is another, this. So there are separate different masks that you need, basically 5 masks that you normally have. Now in case of first mask, so you remember this is the area that is essentially the size of the device. So if you put this mask here, right, so cover this mask here, and then remove the silicon nitride part from the outside, then essentially you get this kind of structure. So silicon nitride is still there, this side you remove, so this part is protected. Now what you do is you get oxidized. So now the whole things will be oxidized, but you remember that this is protected by silicon nitride, so this will not be oxidized. Only thing, the exposed part will get oxidized, and then you grow the oxide layer. So right, so and this one is essentially the very thin oxide layer that you normally use as a gate. So you grow really thick isolation area in this case, and then what you do is you grow another polysilicon layer, right, in this case, and essentially you put another mask here. So this is your area is defined now. This is essentially a gate mask. So you put the mask here and remove this polysilicon layers. So essentially you define your gate at this point, right? And once you define your gate, then all you need to do is that this part, this two part, you have to uh, you know grow basically the n region, right? So since your p type is your substrate, so n type material, so all you need to do is that you have to dope. So this two part you have to dope. Now you have gate, so it is protected again, so only these two parts will be doped, right? And those are basically is going to be like source and drain, right? And then you silox layer, another oxidized layer you grow, and using another mask. What you see is this opening part, which will be essentially contact opening, because source and drain will be connected to this part. So you have open, this is another silox oxide layer, and then finally you grow the metal. So you fill up all the places and then selectively remove some of the part, and essentially you have the device. So you have the two contacts. So now this is your channel, right? This is your gate, source, drain, and gate. So this is how you can actually fabricate the device. Now all you see is you fabricate the device, but there are two uh, separator, low cost separator. Now later, sometime 1980s, so you have complementary MOS, that's the CMOS, right? And the advantage of CMOS is in the same substrate you can have both N-type and P-type transistor, which can be integrated this in this CMOS process. So as you can see here, so this side you develop your N-type, so substrate is P-type, so you essentially have to dope by N-type. Now in this case, uh, N oil or N top. So in this part, since you are going to make P type, so this side we have to really dope by N type. So you convert the whole region by N type material and then dope by P type material. So you have like back to back two transistors separated by low cost isolation. This is oxide, thick oxide layer, and the two transistors can be grown. Now all you need in this case is few more steps and few additional masks. For modern CMOS technology, you would read as high as something like 25 to 60 masks. So it's really complicated process. Now there is another STI, shallow trench isolations, which I earlier told. So essentially, in this case, what are the steps that you do? So it is similar, right? But essentially, first step that you do is that you grow a thermal oxide, which is very thin, 14 to 10 to 14 nanometer, and then you use grow a nitride layer about 100 to 160 nanometer, and then selectively etch out some of the part, dry etch using active area mask, and create a trench, so which is something like 250 to 500 nanometer, and then again you grow an oxide layer by high density plasma oxidation process. So you can grow a very thick layer. So what you do here, that after so this is basically the trench that you make. So you first mask it and then you etch out, then you get this kind of trench, right, which is around something like 300 to 400 micro nanometer thickness, right? And then all you do is that you get oxidized, right? Now when you do the oxidation, then so this is silicon, so you get the oxidized, so you basically fill this part, right? So this part will be filled by oxidized silicon dioxide layer, and then you have two separator, right? So this is oxidized, this is also, so you have to, and this part will be silicon. So eventually you have STI here, STI, so this is where it usually go. So for advanced nanometer CMOS process, both the things are normally used, but this is more popular. STI process. Low cost is, but the thing is that low cost is thick SiO2 that is thermally grown between the active region, but STI is implemented at significantly low temperature. So that's another relatively low temperature processing required for STI based CMOS. Now, before I move to in the next device part, now I just want to show you that when you decrease the size of the device, how the cost increases. Now, as I told in the last slide, that you know in the advance it's much more complicated, right? Design and fabrication part. So more, I mean, reduce the dimension of the channel, your cost increases something like 16 nanometer you see is something like $10,000 million dollar cost, fabrication cost, for 300 millimeter logic fabrication. 300 million, like 30 centimeters, so it's really big region, so it's cost around $10,000 million, so that's quite expensive. Now even if you go further to 12 nanometer device, then it increase even 7 nanometer size also, one can go. But thing is that as you decrease the channel, you are approaching the end of Moore's law, right? Because there are a lot of other processes which I discussed earlier, that when you have a nano transistor where channel length is only tens of nanometer, which I have discussed from these books, atom to transistor, and all the issues in fabrication and the physics behind the charge transport through a small nanometer size devices. There are several issues, of course, challenges, and there are a lot of difficulties in design. The most important part is that when you decrease the channel length, so your thickness of the gate oxide layer decreases with the reduction of channel lengths. Now, what is the consequence is that your channel length is reduced, your gate oxide layer is reduced, but if you reduce the gate oxide thickness, then your leakage current increases, right? So you'll have more leakage current, and therefore the device is not going to work. So and typically, like, increases with the factor of close to 10 for every 0.2 nanometer, further reducing the oxide layer. So if you just decrease the thickness of the oxide layer by zero point 0.2 nanometer, then this increases by 10 times, right? So that's a huge. So that's the major problem, that how do you can reduce the channel length, but how do you grow an oxide, gate oxide layer, because it's going to be very thin, and therefore leakage current increases. So what is important? Important is the capacitance, gate capacitance, which you know that epsilon A by D, where epsilon is the dielectric constant, A is the area, and D is the thickness. Now this D is, you are reducing, your capacitance increases, but leakage current basically also increases if you decrease this. So what you need to do is that you have to compromise between these two parameters, that you can essentially use a higher dielectric constant material, such that you can still go for a little bit higher thickness. So high epsilon is the choice of material, and typically there's high K dielectric materials, which is another field of research, like hafnium oxide, zirconium oxide are basically people are preferring to use rather than silicon dioxide layer. This heavily depends on their mechanical, stress strain, physical, optical, electrical, optical and dielectric property, thermal, temperature, expansion coefficient, thermal resistance, and chemical, lattice matching and adhesion, chemical affinity with adjacent layer. So this properties actually depends heavily on the design of these layers. So you really have to be worried about all these parameters when you really decrease the device size. Therefore, it is a major very important to understand what's going on between metal and the gate dielectric layers, right? So contact and gate dielectric layers, and that consists of a stack of different materials to fulfill all these problems that normally you may come across. So now it is not only one layer, but several layers are considered. Now look at this design of the transistor. So basically your oxide layers comes here. So this is the oxide layer. Now this is going to be the channel, this is source and drain. Now these oxide layers, and essentially now this one can be used either p type, PMOS or NMOS, and they are complementary in nature and require different gate stacks. So it depends on the gate, that kind of gate materials that you use. So it can be either PMOS or NMOS devices, right? So what are the gate stacks? So this is one of the important things. So if you have NMOS, you have substrate. So this is your substrate, and then high K dielectric layer, and then you have another layer with work function 1, then another metal layer, and then the polysilicon. So this is basically your gate dielectric stack. Similarly for PMOS you have different gate dielectrics. Now what is important in this case, in fact, when I discussed about the charge transfer from through a small a small nano transistor, that the work function of the gate material is plays very important role in deciding that the direction of the charge flow, whether it's p type or n type material. So it depends on the work function, so you really have to work on the work function and the different material used for different mass. So all you need to do is to understand and to decide what should be the uh, gate layer stack for NMOS and what should be the gate layer stack for PMOS. Now when you take this kind of materials, different kind of material here, and now remember this is very small nanometer size, tens of nanometer, then there should be some kind of strain developed here in the channel. So for NMOS it is essentially tensile strain, and for PMOS it is basically compressive strain. So this is what exactly happens. Now sometimes you actually use this strain to control the charge flow as well. So what you do is normally strain is essentially a parameters that you make use of it. For example, if you have a silicon lattice without strain, so these are your silicon atoms, so you have some kind of charge transfer. But if you have a strain, let's say it's basically it's a kind of tensile strain, and then your uh, strains of silicon reduce the atomic density and improves the carrier mobility. So that is also another parameters that one uses to. Now strain, as I said, plays very important role in controlling the carrier mobility, and in CMOS systems, as you have provision to develop NMOS and PMOS, so sometimes strain is also used to control the device property. Now what is this strain? Now the strain I explained earlier, that when two materials you grow one after another, let's say you have a substrate which has unit cell this, and that the film that you are growing which is bigger unit cell, so AS is greater than AF, so then there should be some strain, because these unit cells being bigger than the substrate one, so it has to adjust in one side. So if one side it's adjusted with the substrate, then other side would be strained. Similarly you can have the other option, that the film unit cell is essentially smaller than that. So in this case, of course, this side has to adjust, so it should be elongated, and this side should be compressed. So what happens, like when you grow this, then as I said, that in this case this unit cell will be smaller in this side, and in this side it will be elongated. This side will be compressed, this side it will be elongated, and it would be other way around in the case of other thing. So if this happens, then of course you get some kind of compressive strain at this point. Similarly in other case you get basically tensile strain, and because the strain in this side, this will be elongated, this side it will be compressed. So this you can use it, this concept of strain can be used in PMOS and CMOS, PMOS and NMOS fabrication. And what is normally used is a couple of materials. As you can see, the lattice constants for the typical fused semiconductor and carbon material, you see the silicon is something like 5.43 angstrom. Germanium lattice constant is slightly bigger than silicon, it is 5.66 angstrom, whereas carbon is quite small in compared to silicon and germanium, 3.56 angstrom. Now what happens, like if you mix these two material you make an alloy, or this and this two material make an alloy. So in one case your germanium has a bigger in other case the carbon has a smaller. So what happens in for the silicon germanium case, the germanium will be occupied inside the silicon matrix, and therefore it will be like really extended, whereas in case of silicon carbide, then it's like compressed. So when these things happens, then the crystal that you grow, the film that you grow will be strained, and the strain can be either compressive or tensile. So now if you look at the NMOS and PMOS design, then what you see here is, in this case, in case of NMOS, in this case you use silicon carbide. Now you remember the silicon carbide, it has a smaller structure, so you have in this case you have compressive strain, and when you have compressive strain, so you think that this material which is in a channel, so this thing is shrinking down in this way, and therefore this channel material will have some kind of tensile strain. Similarly, in silicon germanium, so this material will be expanded in this way in compared to normal silicon, and therefore there will be some sort of like compressive strain that you develop. So by this two material that you group, silicon germanium in this case and silicon carbide in this case, so you can have like compressive strain and tensile strain in both in PMOS and NMOS.